have to talk about a mole, and a mole is just a number. So just like the word dozen means 12, and the word gross means 144, or a dozen, the word mole means this specific number. The word mole does not imply necessarily what you have that number of. Just like you could have a dozen donuts, or you could have a dozen pennies. You can have a mole of anything. In our daily lives, we don't use that word very often because to have a mole of large-scale things that you would work with, like a mole of paper clips or something, that many paper clips does not exist. Right? Most of the time, a mole is such a huge number. 10 to the 23rd means you've got 6.022, and then you've got to move this decimal 23 times to get all those zeros after the number. It's just an insanely large number. So you're never going to be working with that number of large-scale things. It just won't be that number existing. But since atoms and molecules are so tiny, you can have a mole of them. You can have that number of individual atoms or molecules, and it actually makes up a laboratory scale size quantity. So for example, 12 grams of carbon is a mole of carbon. And since a gram is roughly the mass of a paperclip, that's not that much carbon. So using a mole is actually really convenient when we're dealing with super tiny particles, and when we have a mole of them, it actually makes up enough to be working in the lab. And so for chemists, the word mole, when you hear that word, what you want to think of is number of things. So if I say, I've got a mole of copper and 3 moles of iron, that means I've got 3 times the number of iron particles as I do copper particles. Right? So when you have a mole of something, it relates to the number of individual particles that are present in that item. So this is a nice picture that shows a mole of a variety of different things. So if you have a mole of sugar, in the little sugar cubes, they're not really very densely packed, so it takes up a fair amount of space. Mole of salt, mole of copper, mole of aluminum, mole of water is about a few milliliters there. The gas in the balloon, which is about a mole of helium, takes up a little bit more space, right? Because we know in a gas the particles are farther apart. So in each one of these samples we have the same number of particles, just they're not always packed as closely together, and the states of matter can change. But this is all laboratory size scale things. So when you're doing a reaction or you're doing something in the laboratory, if you need to do it quantitatively and you need to know how much you're working with, a mole is pretty much the unit that you want to be using, because that will tell you exactly how many particles of the substance you have there to work with. So to illustrate how big a mole actually is, let's say we did have a mole of something that wasn't super tiny, like an atom or a molecule. Let's say we had a mole of paper clips. I thought I wrote it in the question, but it's not there. We want to determine if we did have a mole of paper clips, which are about 2 centimeters in length, how many times would it wrap around the Earth? So maybe we want to first make any guesses. Anyone want to venture a guess as to what the answer is before we calculate it? 2 times? Any other guesses? The 2 centimeters, so about a little less than an inch. We don't know, so there's no wrong answer right now. We're just guessing. The Earth is pretty big, but a mole is a lot of paper clips. but we can figure it out. We can do a conversion to figure that out, right? So let's take the time to do this example conversion. So give me a little bit more space here. So if we have 1 mole of paper clips, I'll just abbreviate that PC, and each one paper clip is 2.0 centimeters. We want to know how many times it will wrap around the Earth. So we need some relationships. So if anyone has their phone, help me look up some relationships so I don't have to exit out of this presentation mode. What relationships do we need? 4.0075 billion centimeters. That's the circumference of the Earth. 1 Earth. That's a relationship. What other relationships do we need? Well, yeah, so we will need to know how long the chain will be. So if we're not exactly sure what relationships we need or how to get them, we can kind of set the problem up in terms of saying what are we actually looking for and what two quantities are we trying to put equal by converting the units of one quantity to give us the other new units. So ultimately the question is, how many Earths? That's a unit. Or how many times or how many circumferences of the Earth are we going to get if we wrap 1 mole of paper clips around the Earth? Just so you know, the abbreviation for mole is MOL. So all you do is take 1 letter off. It's not much shorter, but that's the abbreviation. We can't use M for mole because that there are other units that use M to abbreviate for them. So ultimately we're asking, if we have a mole of paper clips, how many Earths is that equal to? So we can use, well, how do we get from this unit of moles to one of the other units? Because we can get to the number of Earths from the number of centimeters, and we can get to centimeters from the number of paper clips. We need one more relationship. We need Avogadro's number. We need the relationship between the number of paper clips and a mole of paper clips. Okay, so not only is a mole a specific number, that number can be used in a relationship. So the way to set that up is the number, 6.022 times 10 to the 23rd, items equals 1 mole of those items. Just like 12 items is a dozen items. Could be any items. In this case, we happen to be working with paper clips. So a mole of paper clips equals Avogadro's number of paper clips. A mole of atoms is Avogadro's number of atoms. A mole of molecules is Avogadro's number of molecules. So that's another relationship. So now we've got the relationships we need. Because I'm starting with a mole, I want to convert this unit to determine how many Earths it will be equal to. So I will use this relationship first. 1 mole of paper clips equals Avogadro's number of paper clips. Right, again, doing conversions, anytime I have two things that are equal, I can put either one on the bottom and the other one on top of it. And since they're equal, I'm not changing the quantity, I'm just changing the units. So now I've changed the units from moles of paper clips into number of paper clips. And I also know from the other relationship we worked out that 1 paper clip is 2 centimeters. So that was given to us as a relationship. So now these units cancel. And we also looked up on the internet, which is never wrong, that 4.0075 times 10 to the 9th centimeters equals 1 Earth circumference. So now my centimeters cancel, I've got the unit I want. So how many times around the Earth, or how many Earth circumferences do we get? We just need to put this in our calculator. So 1 times 6.022 times 10 to the 23rd times 2 divided by 4.0075 times 10 to the 9th, and I get 3.0 times 10 to the 14th Earths. 300 trillion times around the Earth. So obviously there do not exist that many paper clips. Any questions about that? Okay, so a mole is a lot. And it is useful, though, when we have super tiny things, because then a mole of them will actually make enough for us to work with. So here's another example where we can work with a mole. So here's a relationship. Typical human body involves or contains 30 moles of calcium. So that's a huge number of individual calcium atoms. We want to know, what is that number? So if we want to know how many calcium atoms, we could set that up. How many calcium atoms are in a body, or are equal to 30 moles of calcium? So if what I'm trying to relate is the number of items in a mole of items, that relationship is Avogadro's number. Right? So Avogadro's number this relationship is what we use to do conversions when we're working with super small particles like molecules or atoms, and we want to relate that to a laboratory size quantity or a large scale quantity. Right? So if I'm converting from a laboratory scale to laboratory scale, I'm not going to use this relationship. If I'm converting from grams to milliliters, or grams to kilograms, or if I'm converting from grams to moles, which are both large quantities, I wouldn't use that relationship. I use it when I go from individual tiny particles like atoms or molecules to large scale quantities, which is what a mole is, because a mole is a huge number of these things. And that's what I have. I'm converting from something super tiny to something much bigger. That's when I know I want to use Avogadro's number. So I can say that 1 mole of things equals 6.022 times 10 to the 23rd of those things. So the moles cancel, and I just need to multiply 30 times Avogadro's number, and that will give me my answer in atoms. Questions about that? Slightly different example, where in this case, instead of converting from moles to individual particles, I know how many individual particles I have, and I want to know how many moles that is. So I can do the same relationship, but in the reverse direction. So if I know I have a specific number of tiny things, and I want to know how many moles that is, which is a very large thing, a very large quantity, I would use Avogadro's number in this case, except in this case, I want to get moles of calcium, and I want to cancel the individual atoms. So I will flip the relationship anytime two things are equal. I can put either one on the top so that I get the undesired units to cancel. And so in that case, I would divide 1 times 10 to the 20th divided by 6.022 times 10 to the 23rd. And now we get 0.000167166 moles. Any questions about that? Okay, I forgot to mention, this is an experimentally determined number, Avogadro's number. It's not an exact number. It's not a definition. So it doesn't have unlimited sig figs. Usually we limit it to 4 sig figs because most of the time measured data is going to have less than 4 sig figs. So we don't want this number to limit the sig figs in our answer. But there is a limit to how many sig figs it has. It's been measured to a lot of sig figs because we have really precise instrumentation. We can measure that and get a lot of known digits in there. But it's not an exact number. It's not a relationship. So when we do use it, it could potentially limit our sig figs. So if we're looking at sig figs here, this one limits me to 3 sig figs. So I'm limited to 3 sig figs in my answer. Avogadro's number, I usually use 4 sig figs.